All right, this video goes with the day one notes review of parametrics. So you'll want that packet out as we go along. Now you should have learned all of this in pre-calc honors last year, but we'll need to be solid with it for this unit. So this video and the other video will help make sure you are ready for that. So an object is propelled into the air from ground level at an angle of inclination of 45 degrees, and that is shown in the diagram. We've got our initial velocities 48, and the horizontal and vertical positions are represented by the parametric functions listed there for x of t and y of t. So x of t represents the horizontal component of the object's movement, where y of t is the vertical component of the movement. So using those functions, we want to eliminate the parameter t. So to do that, we can just work to get t alone in the top equation. So that would make x over 24 radical 2 equal to t. So we can take y and sub that in for t in all the spots. And if we were to square the 24 square root of 2, and then do negative 16 divided by that, we would get negative 1/72 x squared. Over in the other part, the 24s divide to 1, the square root of 2's divide to 1, so we just get x. Going to the next page, we can see the graph of our function that has only y and x in it. Now the graph of the parametric function would actually be exactly the same. Now both functions tell us where the object is located. The thing about the parametric is it can also tell us when it is located there. So the time that will put it at that location. Whereas if we're just in terms of y and x, we cannot do that. So if you could take a second and take your calculator out, we're going to learn how to put a parametric equation in the calculator. So we got to go to a graphs page. We'll go menu, graph entry edit, parametric. Now notice our variable is a t here. So we need to make sure we use the t when we're putting it in. So our x component was 24 square root of 2, and then t. And we'll put in our y component, our negative 16 t squared plus 24 square root of 2 t. And we want to change our t specifications. So we want to do our t's from 0 to 4, it says. And we want to do our t step as 0.1. Okay, and then it wants us to adjust our window. So we can go menu, window zoom, window settings. We got an x min of -1. X max of 100, Y min of -1, y max of 25. And we now get a picture of our graph. Now, what's nice about the parametric is if you go menu and then trace and do graph trace, notice as you move your cursor, it'll go by our step that we told it, 0.1 for t's, and it will tell us our x's and our y's that correspond to that. Okay, so again, that was menu, trace, graph trace that can get us each of those values. All right, going back to the packet, we have that picture of the graph there that's showing us the same thing. So we want to know how long in seconds is the object in the air. Well, if you are no longer in the air, that means your vertical component, the y, is 0. So all we'll do is we'll take the y part and set it equal to 0. We can factor out a t. You can take out an 8t if you even wanted. Maybe we'll do that. So that would give us negative 2t plus 3 radical 2. If we set these equal to 0, this will give us t equals 0. And if we solve for t here, we'll get 3/2 radical 2 seconds. Well, this is where we started, so we want this one when it is hitting the ground. Alrighty, going to the next page. So we're given an equation in rectangular form. Okay, when it's x's and y's, that's called rectangular form. And we want to rewrite this in parametric form. Well, the technique you learned last year is to just let one of the variables equal t. Because y has stuff being done to it, it's probably easier, in this case, to let y equal t. Then subbing that t in for y, that just tells us that x is equal to t squared. So that would be how you would switch from rectangular back to parametric. Just let one of the variables be t, and then rearrange the other one if you have to figure out what it is. So we've got a t table here. So our y's are just t, so we can copy those down. And our x's are just the t squared. And we'll graph that over here. Now as you're plotting it, take note of which direction the points are going as t increases. So we're starting out with 9, -3. Then we've got 4, -2. 1, -1. And these are the rectangular points we're plotting. 0, 0, 1, 1, 4, 2, and 9, 3. Now keep in mind, we could have kept going with our t's, so those points really aren't endpoints. And then you have a parametric function, you have to draw in the orientation. So the orientation, we represent that with arrows, and that tells the direction we are going. Well, as we were plotting the points, we were going this direction. So we would put some arrows on going this direction, and that shows the orientation of the parametric function. So as time goes on, we know which direction we are moving. All right, down on the bottom, we are given the parametric functions. We need to rewrite it in rectangular form. Well, instead of getting t by itself, notice y is just 2t, so we can replace the 2t with a y. So that would be just x equals y squared. And then if you wanted to get y alone, y is just plus and minus radical x. Well, if we're to sketch this one, maybe we'll start the y's again. It's just double the t's. So I have minus 4, minus 2, 0, 2, and 4. And then the x's are just those squared. So we'll plot these now, and I'm going to scale mine by 4s on the x-axis. We'll just go by 1s on the y-axis. So we have 16, which is out here. Oops, we got to go to negative 4, so I need some more. So we have 16, negative 4. We've got 4, negative 2, 0, 0, 4, 2, and we've got 16, 4. Again, we could have picked more t's in either direction, so those aren't really endpoints. We would want to put our arrows in. And then how is this plane curve similar? How is it different? So a plane curve is just what you call the graph of a parametric equation. So I think that was on another slide, but I forgot to mention that. But that's just our graph of a parametric equation. So we can say that it's the same graph, meaning x's and y's, and the same orientation. However, something that's different is there's different t's that are corresponding to the rectangular points. Like up here in the last one, it was negative 2 that gave us 4, negative 2. Well, now it's negative 1 that gives us 4, negative 2. So even though the path of the object is the same, the time that the object is in those locations is not the same. So we can say different t's for the rectangular points. So the orientation and marking that on the graph is key for parametric functions. I should say parametric equations, they're not necessarily always functions. That last one was not a function. So state the domain in terms of t. So we need to think about what issues could we have. Well, in the x, we need to make sure that denominator is not 0 because it's in the denominator of a fraction, and the radical also has to be non-negative. So in other words, the t plus 1 always has to be positive. Well, another way of saying that t plus 1 has to be positive is saying t plus 1 has to be greater than 0. So in other words, t has to be greater than negative 1. Well, in the y, the only problem we had to worry about was the negative 1. So t being greater than negative 1 means we're in good shape. All right, so to put this in rectangular form, we need to get one of the t's by itself. We'll maybe work with the x because that only has one t. Well, if x over 1 is equal to 1 over radical t plus 1, we can do the reciprocals, and 1 over x will be equal to radical t plus 1. You can put it over 1 if you want it. We can square both sides to get 1 over x squared equals t plus 1. And we'll end up getting 1 over x squared minus 1 is equal to t. So we can go over to our y, and anywhere we see t, we will put that in. So we'll have 1 over x squared minus 1. That's all over a 1 over x squared minus 1, but then the plus 1's there. So those add to 0. So we really just have 1 over x squared minus 1 over 1 over x squared. Well, we can neaten this up a bit. Dividing by 1 over x squared is the same as multiplying by x squared. And if you distribute that x squared through, we'll just get that y is equal to 1 minus x squared. So that would be the rectangular form. So if we go down to the bottom, continuing this problem, we're going to end up graphing this, but we need to think about a couple of things. We need to think about some limits. We want to think as t goes to infinity. So that would tell us with our orientation the direction we're going. So as t goes to infinity, as t becomes huge numbers, so our limit as t goes to infinity, and we want to think about x of t. So in that radical, the t's become huge, plus 1, you'll take the square root, so we're going to have 1 over huge numbers, so that will head to 0. We can do the same thing for y of t. Well, we have the same degree, so we can do the ratio of the leading coefficients, which is just 1. So oops, I forgot my infinity there. So as t goes to infinity, we should be getting closer and closer and closer to the rectangular point 0, 1. Well, notice, like for example in the x, there is no way to actually make that be an x value of 0. And that's because in the numerator we have just a 1. So this 0, 1 is going to be a point that we're going to get closer and closer to, but we'll never hit. So it's essentially going to be an open circle. Now the other thing we have to be concerned about is that domain that we had from above. We had t is greater than negative 1. So we can only have t values on the right side of negative 1. So we want to think about what is our limit as t approaches negative 1 from the right. And we'll do it for x of t, and we'll also do it for y of t. Well, negative 1 from the right would be like negative 0.9999999. If you put negative 0.999999 in there, we're going to get a really tiny positive in the denominator. Well, 1 divided by a tiny positive, that's like having 1 over 1,000. If you do a keep change flip, that'll be a big positive. If we have negative 0.99999 for the y, the numerator is going to get really close to 1. So that's not an issue. So the denominator, though, is going to be really tiny positives. Negative 0.9999 plus 1, think of it as like 1 over 1,000. When we do keep change flip now, we'll go to negative infinity. So what this means is the graph should be coming from the right for the x's, because we're coming from positive infinity, and coming from the bottom for the y's. So our graph should look something like this, with our orientation going in this direction, because as we go towards infinity, we should be approaching 0, comma 1. Now, if we wanted to get this graph more precise, t has to be greater than -1. Imagine if t was 0. If t equaled 0, x would equal 1 and y would equal 0. So if we wanted to get more precise, we could label that point there as 1, comma 0 also. All right, that's it for the video for day 1.